So now I'll go through a quick example of solving an optimization problem using Lagrange method. So suppose I want to find the minimum and maximum values of the function 4x2 minus 2x3. So this is a function of three variables, x1, x2, x3. But the first one in the objective function, it just has a 0 multiplied by it. So I'm going to simplify it just to say 4x2 minus 2x3. Then subject to the constraint 2x1 minus x2 minus x3 equals 0. So I've written the constraints equal to 0. And the constraint x1 plus x1 squared plus x2 squared minus 13 also has to be equal to 0. So the first step is just to write down the Lagrangian. So if I have two constraints, the form of the Lagrangian is going to be objective function plus lambda 1 times the first constraint plus lambda 2 times the second constraint. And then I just have to substitute these things in. So f of x is my objective function. That's 4x2 minus 2x3. So that's what I've put here. Then minus lambda 1 times the first constraint. Plus lambda 1 times the first constraint, plus lambda 2 times the second constraint. And then I need to also check my necessary condition. So if I look at the gradient of the first constraint is going to be 2 minus 1 minus 1. And the gradient of the second constraint is going to be 2x1 plus, or 2x1, 2x2, and 0. And so you have to just look at this a little bit and convince yourself that it's always going to have pivots. So one way this could not have a pivot is if x1 was equal to 0 and x2 was equal to 0. But if that were the case, I wouldn't satisfy this constraint because negative 13 would not be equal to 0. And then if x1 and x2 are any other values, and I get this 2 as a pivot for free. If I did any sort of row operation with this row, I would turn this 0 into something else. So if I had to do a row operation to get a pivot here, this 0 would become non-zero. So it's a little bit of you have to make a little bit more of an argument. It's not something you can always just see very clearly that this condition is going to be satisfied. But you should, well, I guess it would be a good habit to check. Okay, so start off with the Lagrangian that I had on the previous slide. And I'll compute the gradient of the Lagrangian. So I'm not going to do the matrix vector notation. This is a function of 5 variables, so I'm just going to do the 5 partial derivatives one by hand. And just to make it fit on the slide, it was too wide as a row vector, so I wrote it as a column vector and then transposed. And to find the critical points of the Lagrangian, I now have to solve for lambda 1, lambda 2, x1, x2, and x3 to make this vector equal to 0. So sometimes you get a little bit of help. So I can look and I find the middle row here, row number 3. If I set this equal to 0, there's only going to be one value of lambda 1 that's going to make that equal to 0. So I get one of the ones for free, but now I'm going to have to do some work to get the rest of the values. So I get lambda 1 equals negative 2 for free. And then I have to take the other rows and set them equal to 0. So once I set these equal to 0, then I have 4 equations and 4 unknowns. They're not linear anymore, so there might be multiple solutions to this. So for instance, the last equation has x squared and x1 squared and x2 squared in it. But I can do some simplification because I know these lambda 1s, they're going to be equal to negative 2, so I can substitute in a negative 2 to get myself out of a little bit of work. But I have to find lambda 2, x1, x2, and x3 that are going to solve this. And the other tricky part is not only have to find the solution, but I have to find all of the solutions, because the only guarantee that I get is that the optimal value, the critical points are going to include the extreme values. It doesn't tell me that once I have one of those critical points, whether it's a maximum or a minimum. And so if I find one solution when I'm looking for a maximum, and that one just happens to correspond to a minimum, then instead of solving the problem, I've actually found the worst possible solution for any other vector would be better. So you have to not only find the solution to this, but you have to find all of the possible solutions to this. And so if you do a little algebra, which I decided to skip in the interest of brevity, you can solve for x1, x2, and x3 in terms of lambda 2. And so you end up with these three expressions for x1, x2, and x3. And I got those just from the first three equations. And then I'm going to combine that with the fact that I know x1 squared plus x2 squared is equal to 13. So I can plug x1, so 2 over lambda 2, in for x1 here, and minus 3 over lambda 2 in for x2 here. And what I end up getting is 13 divided by lambda 2 squared is equal to 13. And so that tells me that lambda 2 squared has to be equal to 1, and that lambda 2 is then going to be plus or minus 1. And now because x1, x2, and x3, they're functions of lambda 2, it means I'm going to end up with this. So the lambda 1, that's fixed at negative 2. That will always be negative 2. Then my other critical points are going to be lambda 2 equals positive 1, x2 equals 2, sorry, x1 equals 2, x2 equals negative 3, and x3 equals 7. Or lambda 2 equals negative 1, and then I'm going to get negative 2, positive 3, and negative 7 for my x1, x2, x3. So these are the two critical points. And then if you evaluate f at this critical point, so this lambda, kind of once I'm using that as a crutch to get myself to here, but once I've got the critical point for the x's, those are actually the ones I want to evaluate, because I'm trying to find the maximum and minimum value of this function f. So then I just have to evaluate f at all of those critical points that I found. And then whichever one is the biggest, that's the maximum. And whichever one is the smallest, that's going to be the minimum.